Okay, so our next speaker is Edgar Dobriban, who's a professor at the University of Pennsylvania. He's going to be telling us about a theory of nonlinear feature learning with one gradient step in two-layer neural networks. So the floor is yours, Edgar.
All right, thank you. Thank you very much for the invitation. It's really a real honor to be here. And, obviously it's a beautiful place and wonderful research happening on this campus. Let me see. The clicker is there a clicker? Or it was yours? Okay, maybe this one works for me. Okay, maybe this one works. Okay. It's fine. Yes. Okay. Maybe I'll use it for now. Okay. So first of all, I'll be talking about this work, which is a joint work with my collaborator and friend Hamed Hassani, who many of you might know. He got his PhD here actually, and some students. Behrad is working with Hamed, and Dongwan is our jointly advised students, both really talented. And so I have some high-level slides at the beginning. As we all know, the reason why we have some interesting theoretical things to talk about is because empirically deep learning is very successful. The engineers really make things work. That's why it's kind of so everything works. Theoretically, there's a lot of mysteries. We are fitting very complicated optimization. Very complicated architectures, highly nonlinear, hugely non-convex. There's no real, reason why it should work. A lot of theoretical methods have been developed. Here's some sort of high-level theoretical things that have been developed. The notion of compositional architecture is kind of really somehow fundamental. Maybe intuitively you can think if you can process your data to get from some stage, it's images, you process, extract some features, then based on that you process and you can do image classification afterwards. If you can get from A to B, you can get from B to C. Deep learning promises you that you can get from A to C just by composing them. It's very, very, very naive, but I think it's actually probably a lot of the success is just this. There's a lot of approximation theory results. We've already heard a little bit about some algorithmic or implicit biases where somehow gradient descent does something magical, that it produces a low complexity and beneficial solution. There's results about maybe deep learning somehow adapts to the structure of data. If there's some sort of low-dimensional manifold, then it is able to leverage it better than some kernel, perhaps. And feature learning, where the neural net somehow is extracting some useful feature automatically from the data. So these are just some high-level explanations. I'll talk about feature learning today. So it's a little bit hard to see, probably, but here's some tiny faces. After a few layers, the neural net extracts some sort of pattern of local contrasts. That's kind of in the activations of the neurons here. Few more layers, it extracts some face features, and eventually it is able to kind of really reconstruct the faces to a high accuracy. And then afterwards, you can train anything on top of it. You can, let's say, make it a classifier, or detect the objects, and so on. So I just went online and just searched why does deep learning work. It's like, okay, to the general public, maybe they might do that. And Google, even though it can be problematic recently with its AI answers, it's just suggested it extracts deep learning useful because it extracts features from data. So to the public at large, 99% of the population, they might think that this is one of the reasons why it works, and probably there is something to it. So, and I'll go, talk about our work. I'll present a lot of context about related work, but we, in our paper, we provide some theoretical explanations. showing a form of non-linear feature learning. So that's really our work, the content of our work. So we consider simplified models that we can analyze theoretically for the purpose of this work. Two-layer network, fully connected, and sort of the same, similar proportional limit asymptotic as Yue was talking about, everything going to infinity proportionally. But we also have a lot of limitations, including the fact that we consider some non-standard training procedure that I'll explain, and we also consider unstructured isotropic data. So these are not great, but it's just one step in the kind of research process. Okay, so we all know two-layer neural nets. So let's say we take a d-dimensional vector x, and x sub 1 up to x sub d are the coordinates. Then it gets mapped through a matrix W, an capital N by D matrix, to map into Wx, and then there's some nonlinearity sigma that's applied element-wise to the coordinates of W times x to get the feature values f1 up to fn. And then finally, there's a readout, or a last linear layer that maps this linearly into one output vector, scalar y. So, and there will be a sample size lowercase n, and all three of these sort of quantities will be taken to converge to infinity at a proportional rate. So we will study d by n converging to some phi, and d by capital N converging to some psi. So for theoretical analysis purposes, the simplest version of this sort of architecture is a kind of a random feature model, where this W is generated at random. Maybe think IID Gaussian entries with some variance, and then it's fixed. It's not trained. And that can already have some benefit. It can be viewed as a finite rank approximation of some kernel methods, so it can be also useful. But theoretically, it's much easier to analyze. Unfortunately, as the name says, it's a random feature, so there's no feature learning going on. Nonetheless, this is already, there's lots of papers on the random features model. It already has some, lots of interesting behaviors. Here I list some papers, many more papers in our in our own, related work section. But this has already been used to analyze a lot of things. On the other hand, it's known that in this sort of proportional limit regime, the random features only extract a linear component of the target function. And I list here some papers, including from Yue and Hong Hu, and some other papers from Andrea Montanari and so on. Now, sort of same equivalence that you had presented here. It takes the following form. So basically, what's going on here? When I apply this sigma to the Wx, roughly speaking, under this proportional asymptotic regime. First of all, I can take this sort of Hermite polynomial expansion. Sigma of Wx is exactly equal, maybe in some L2 sense, or to C1 Wx plus C2 of the second Hermite polynomial Wx, and so on. And roughly speaking, everything behaves as if this nonlinear component was IID Gaussian noise with the appropriate variance, right? So this kind of principle can be applied here, and basically you're hoping that you extract some nonlinear feature, but in reality you just have linear. Like you haven't done anything really. It's just a linear feature, and it's even worse because you just add noise. So we want to have feature learning, want to understand feature learning. So we need to go a little bit beyond, and we would like to do our best, of course, but full kind of realistic training, including all batch size, learning rate decay, Adam, whatever. It's very hard. So we are going to do something simpler. I want to highlight here a few methods for a few kind of theoretical frameworks that can have feature learning. One of them is this kind of nice framework of tensor programs, Greg Yang and collaborators. They won't have time to go into it, but that's one way, one theoretical mode of analysis in which you can have feature learning. And another one is about one step of gradient descent, or a few steps of gradient descent, on only the first layer of the weights. And this has been studied in a few papers, including from several speakers, Alex, Damian, and Florent and Lenka's group have several papers on it, and this one from Murat Erdogdu and collaborators, Jimmy Ba and so on. So that's what I will do as well. That's what I will study as well. So how? By the way, please feel free to ask questions at any time. As a relatively informal. Hope that you learn something from this, or enjoy it. Okay, so this is how we do the sort of one step of gradient descent. So okay, we have to initialize somehow. So we initialize the second layer sort of linear readout by some Gaussian, and we initialize the weights also in an IID Gaussian way, and then we update the weights by taking the gradient of the empirical mean squared error loss on some data set. I'll explain how that data set is generated in our theoretical analysis, but here is just some XY, XY pairs, and we take a learning rate eta and take one step. So in contrast to realistic training, this eta will be quite large. That's why there's paper that says one giant step at a time. So it's a large learning rate here. And we also the other sort of non-standard thing that we do following some of these papers is that we actually consider sort of sample splitting. There's a second independent data set, and then we fit the second layer weights alpha hat by ridge regression on that second layer, on that second independent data set. So y tilde and x tilde are data set of the same size. Here we don't consider, you could look at slightly different sizes, but this is what we do here. So is this, did I explain this sufficiently clearly, or do you have questions? Okay, pretty clear. All right, so now for the purposes of our theoretical analysis, we will assume pretty standard theoretical assumptions. So the data points xi will be IID standard normal, as in US talk. This has no structure. Of course, it would be interesting to have some structure, but no structure here. And the yi will be generated also IID from some nonlinear function of the xi's. I'll talk about what the nonlinear function is. And sigma epsilon squared will be the IID, the variance of the IID Gaussian noise. And so basically we have two n data points, and we just put the first n of them into xy and the second n of them into x tilde y tilde. So there's a so it's known from this relatively recent paper that rigorously known that only a single index approximation can be learned under this proportional limit asymptotics. So basically, if I have basically that tells us that we can restrict to functions of this form, where there's there's a linear projection of the xi into some direction, and then a nonlinearity applied to it, and that's kind of captures what can be learned under the model that we have described with proportional limit scaling. So it's just a question of, can we learn beta star, and can we learn the nonlinear component of the sigma star? Yeah.
Is there some commitment to standard or mean field scaling in this one-step context?
In our theoretical analysis, it will be mean field proportional limit scaling. But you could potentially analyze it under different settings, but we just analyze it under this setting. By the way, when I hear mean field, I'm not a physicist, so I'm not sure if we're speaking the same language, but I think I speak.
Yeah, like in Montana.
Yeah, exactly.
Because we are confused among ourselves as well, because we also use it in different contexts. So in that particular case,
Yeah, so I want to make sure that I understand. Okay, yeah, but I think, yeah. All right, so for us, kind of very important prior work was this Ba et al. Paper that studied essentially everything exactly the same as us, but it took sort of order one. First, they took order one steps, and they showed that there's no nonlinear feature learning. So in fact, this is really limited, and you don't even do better than a linear regression on the full data. That's a kind of very low bar. They were able to show that if you take the learning rate to be order square root of n, then you can in fact go beyond linear and kernel predictors, but it's not clear by how much. So it's kind of limited understanding on that front. So this is really where we kind of got started and this inspired us to think how and what is going on here, what features are learned, and by how much performance can improve. So this really what we started with, and we got some insight that I was kind of happy about in terms of spectral analysis of the feature matrix. So here's how a little bit of how that goes. So there's the W 0, and okay, there's the gradient of the loss, and it turns out that from this paper, essentially, by looking at it and kind of analyzing it a little bit, it can be shown that this is a rank 1 matrix. So the way it looks is that there's a W0 plus this rank 1 update. And so if the eta is sufficiently large, then there's the in a singular value space. If I look at the singular value of the W0, I get what you introduced, the Marchenko-Pastor. The singular values have the square roots of the Marchenko-Pastor sort of density, and then there's the rank 1 spike if the learning rate is sufficiently large. So there's some sort of something here learned, and it's easy to see that this quantity x transpose y is sort of highly correlated, or it's correlated with the true beta star. So this is what the one-step update does to the weights. But what does it do to the features? So that's quite one can figure that out. So I apply this nonlinearity to the matrix, and what's going to happen is in terms of individual elements, actually, the individual elements of this matrix are quite small compared to the individual elements of this matrix. So actually, one can think about a sort of Taylor or some other series expansion, and in fact, that leads to a number of terms which can now lead to multiple different spikes on the in the F matrix. So it turns out that the number of spikes that you see depends on the scaling. If you take, we're gonna take eta, the step size, as a function of n to the alpha, where alpha can have different regimes. So let's say here it's between 0 and 1/4. Then turns out, I'll talk a little bit about some heuristic, but you can see that there's only one spike coming out in the F. If you take it a little bit larger, between 1/4 and 1/3, then you see 2 spikes coming out, and so on. So you get this sort of spike matrix, and there's a sort of some sort of a phase transition, like the famous Baik-Benaru phase transition. Although we don't have such a clean description of the phase transition, we only consider things in between. So it's kind of easier to do that in yeah. Yes, I'll show you next.
So what about just the bulk? Is the largest eigenvalue of the bulk sticks to the edge of the spectrum? Is that rigorously proven?
No. What we at least.
Can you repeat the question?
Oh.
Yeah.
Oh yeah. So the question was, which part of this picture is rigorously proven? So for instance, is it known that? So what? Okay. So that just the bulk distribution is Marchenko-Pastor. That's known. But the fact that the operator norm sticks to the bulk, I think that's not exactly known. It's just that it's of order square root of n. So we will analyze things in a way where the spikes will be order-wise larger than order square root of n. So it's going to be, yeah. So that's what I'll get to now. And essentially, kind of intuitive picture is that this nonlinearity, so in the weight matrix, there's only a linear spike, but the nonlinearity pushes this nonlinear spike kind of outside of the spectrum and creates these nonlinear features. And that's how we can say, okay, there's nonlinear features being learned. Okay, so now here's one sort of theoretical result that maybe partially answers the question. So remember, F0 was the untrained or random feature. F was the trained feature, which roughly is like this. Then we consider the Hermite polynomial expansion of the sigma, the activation function. Ck are the coefficients. And this is our sort of theoretical result, that if eta has of the form n to the alpha, where alpha is in between, essentially 1/2 minus 1 over L and 1/2 minus 1 over L plus 1. Maybe there's a factor 2 there. Then basically under some conditions that I'll talk about later, I'll write down the rigorous conditions, the difference between the operator norms of F and this sort of finite rank approximation that I'll explain in detail is of little OP square root n, whereas everybody here has eigenvalue operator norm of order square root of n or higher. So this one is of order square root of n. This one could be of order, they are of order actually in our scaling guaranteed to be of larger order than square root of n. So basically this is small. So okay, so now what's going on? What is this finite rank approximation here? So okay, so you can see F, and you're tempted to expand the series here. You look at the first few elements of what happens. So because sigma is applied element-wise, the things that we get in the spikes are also element-wise powers, and those can be so x tilde beta to the this is to the power k element-wise, and a to the k is also element-wise. So you get kind of outer product of two vectors raised to the kth power element-wise. And these are just the natural things that you get, c1 to the power k, and this is coming from, this c1 eta here is coming from just being raised to the power k, and ck is the expansion here. So this sort of rigorously proves in certain regime, and notice here we avoid the hard cases, the edge cases, where there's equality, it's strictly in between, that nonlinear features are being created. Okay, so that's, it was, I was pleased to see this. And then, but this doesn't show anything about, the test loss or, the kind of real learning component. Yeah.
Just a pervert question.
Yeah.
Even in this case, when what we used to call the information, when C1 is 0,
Mm-hmm.
your sigma is H2, let's say.
Right.
Then this whole thing just disappears.
I think so.
But something must remain.
Yeah.
It takes much longer to, as we used to call, escape mediocrity, but something remains.
Yeah. I haven't thought about it. I apologize, but I think it's a very, it's a really fundamental question. What happens? Yeah. Yeah. No, but yeah, you're right. Honestly, even I even haven't thought about what happens here to the rank 1 update, and how, yeah, that's a good question. Okay. Yes.
Question. So is it possible to see this numerically? Because I would imagine if you have L equal to 4, then it depends on a really precise alpha, right? Because the two bonds are very close.
Yeah, it's
very large.
Exactly. So I'll show some simulations at the end. Fortunately, I don't have the spike just for the MSC, but it's very hard to see for larger ranks. As you noticed, you need to take n to be really, really, really large to see this phenomenon. Yeah. So yeah.
So you might have said it that I missed, but if I look at the strength of the outlier in sigma compared to the bulk,
it's a function of it's a function of this eta. It's going to be n to some power. It's going to be n to some power which is larger than 1. So the spikes are exploding if you know.
But not necessarily the square root.
No. Oh yeah, exactly. Not the square root. We don't go up to that limit. In this paper we're not able to analyze. It would be alpha equals 1 over 1/2 essentially. And there's a nice recent paper from I think everybody in the first row and plus a bunch of people in the second and third rows that handles that case. Yeah. So here for there would be somehow too many spikes for us to analyze well from this perspective. Yeah. Okay, this is sort of the picture. Okay, and let me see. In terms of time, I still have 15 minutes, maybe. 15 minutes? Yeah. Okay, so just in terms of some very brief intuition to see that this really makes sense easily, if I consider the norm of this quantity, I mean the operator norm of this rank 1, let's just take this rank 1 term, C1 and Ck are of order 1, so that's okay. Then eta to the k, that's n to the alpha k. Every entry here is of order 1, so the norm of it is square root n. Every entry of a is 1 over square root of k, so the norm of it is square root n minus, square root n times n to the minus k over 2. So it's of this size. So if I just ask myself, how large do I need, let's say k to be such that this is much larger than square root of n, and order-wise it pops out from the bulk, then by some calculation I can see that, straightforward, that alpha has to be larger than exactly this term. So, this is the only calculation whose details I'll show because it's easy and because, it gives some intuition and reaffirms that this makes sense somehow.
Also, in the same vein, if your sigma, if you try to choose a good sigma, if your sigma is a polynomial, then your Ck will be 0 after a while.
That's right.
And then you lose everything else.
What do you mean by I lose everything else? Oh, that's right. Yeah, exactly. Yeah, right.
If your sigma now is a polynomial of 3, 5, you cannot find more than 20 things.
That's true. Yeah. So maybe with multiple gradient steps or some other mechanism, it's possible.
But maybe it's just an argument to not take a polynomial sigma.
Ah, I see. I like that. Yeah. Yeah, that's nice. Okay, and then so some consequences for the training and test error. Ultimately, that's what we want to analyze. So we would like to proceed by leveraging this insight first. That if we replace the in some formulas for training and test error that we can derive, if we replace the nonlinear features by the spike approximation, and then if we replace the random features with the sort of linearization, then the formulas are unchanged. So this is roughly how we analyze it. This second step requires some extra work, which I'll talk about in a second. But ultimately, we can show a result of the following form. In the same setting as before and under the same conditions that I'll just introduce in one slide, then basically we show that the learned features improve the training error compared to the random features by some amount. I'll show the formulas. And the same thing for the test loss. Test loss, it's a little bit complicated, so we only work out the results for 1 and 2, and in fact only prove it for 1 and 2. But there's been a recent very nice work that I mentioned that has a formula for alpha equals 1/2, even like more general setting. Typo, we have some very interesting idea of a kind of spiked random feature model, and they handle that case, so that kind of essentially supersedes a lot of our results. But anyway, so here's those conditions. So as I mentioned, f star, the true function, is of this form, single index function. So beta star we assume to be to be a Gaussian vector, and theta, Lipschitz, of a constant Lipschitz parameter. The activation function, teacher activation function, also has a Hermite expansion with this norm. And then the activation function that we use for learning, as I mentioned, it has an Hermite expansion, and we need some decay condition, essentially, like Gerard was saying. In order to truncate and control the error terms, we need them to decay kind of sufficiently fast here. And we need 3 derivatives that are bounded. Okay, so then here's some formulas, just to show you that we can derive them. So how much does the training error improve compared to untrained features? It's by this much. So what is psi? Psi was the dimension divided by inner layer size. Lambda is the regularization parameter, ridge parameter. C star 1 is the linear strength, the strength of the linear component in the true teacher function. M2 is something else, some Stieltjes transform I'll show in the next slide. Phi is this d by n, and C star 1 is the same thing. C star is the norm of the teacher function, and sigma epsilon is the Gaussian noise level. So what you can stare at this and say, well, okay, if this norm is fixed, and I have an increasing C star 1, meaning I have a larger and larger linear strength in the teacher function, then I'm learning more and more. Okay, you can analyze something like that. And then for the second component, you have delta 1 plus delta 2, and delta 2 is this. It's very complicated. I mean, it starts to get more complicated, but you can see the key thing here is this C star 2, which is the strength of the quadratic or component. So basically, it's saying that if I have larger and larger quadratic term in the teacher function, then I learn more and more. Okay, exact formulas are not that crucial. So what are those M1 and M2? Essentially, they're the quantities derived in this nonlinear random matrix analysis that you mentioned in these 2 papers. I found them, and they're just the limit of F0, F0 transpose, so the Stieltjes transform of this F0 matrix, and this M2 is scaled, everything scaled. Maybe there's a 1 over something here missing. And there's some extra X tilde here. So exact formulas, they are known, and one can solve them numerically. Okay, for the test error, I have a similar formula. I won't spend time on it. There's some derivatives here. And unfortunately, for the general case, it's a little bit complicated. We don't have to go through the formula, but we can get a formula for any basically learning arbitrary kind of polynomials of arbitrary order. And you can see that the error term is something a little bit, a bunch of sums here, and there's some matrix inverse, and there's some xi's, which are the expansion of the xp into the Hermite sort of basis. So exact formula, I don't really know how to interpret it, but this is what we get. And it's consistent with the staircase property that sort of you mentioned, that if I take, probably the intuition here is that I take more and more small gradient steps, I learn more and more. Here we analyze one large gradient steps, and I think about it as the larger the gradient step, the more sort of small gradient steps it corresponds to somehow heuristically. But it's between different ranges, regimes of the learning rate, I learn more and more of the true target function. Okay, so in the proofs, there's a few steps. We use our equivalence theorems to replace f with the spiked approximation. We use some Woodbury formula to expand everything and get it in terms of the F0 transpose. And then there's some quadratic form as in some vectors that appear and in this resolvent that we need to analyze. So these are the ones that kind of we spend the most time thinking about. And this is where we want to take the want to use the Gaussian equivalence to move from the nonlinear matrix to the sort of linearized matrix, but we couldn't use any of the existing results. We can talk. I can talk more. Happy to talk more offline. See if somebody knows how to use existing results, even though they weren't directly applicable. Essentially, well, okay. So first, after we do the linearization, we can reduce everything to Adlam and Pennington and other works to find the things in M1 and M2. But in any case, here, even though we weren't able to use the existing results, we followed essentially similar sort of principle by some Lindeberg exchange method and some concentration and some results from El Karoui's spectrum of nonlinear kernel random matrices. So that's just the highlight of the proof. So simulation-wise, what can we see? Let's say we look at two cases only for simplicity here. One of them is a linear teacher function, and the other one is a quadratic teacher function. So what do we expect? We expect that for the linear function, we do learn something linear, but then for the quadratic, we learn something even more. That's sort of the idea, and this is what happens. So here, this is the training error, and here is the learning rate on the x-axis. On the y-axis, you have, as I mentioned, training error. So you can see you learn something for the linear component, and that's the blue one is the linear. And you see here you learn even more. And you can roughly see sort of it's at one, it's not precise, but it roughly happens where it should happen here at 1/4. In any case, the point is with a quadratic teacher function, you can learn more by this one step of gradient descent. Same thing for the test error, although there's some overfitting here. All right, so to conclude, I presented some results that showed nonlinear feature learning with one step of gradient descent. It's very interesting to think about here how the features depend on, the learned features depend on the size of the gradient, step size. Yeah, that's it. Thank you very much.
Any questions for Edgar? Yep.
What if you do 17 steps?
I don't know, but depends how hard you're willing to work. It depends how hard you're willing to work. I don't know. Yeah, it gets very complicated, and yeah. So I don't expect something super fundamentally different from a finite number of steps. Yeah.
Is it clear that the dynamics is stable with all these different power law for the learning rate, that nothing explodes?
In what sense stable?
Well, if I train a network and put a very high learning rate, I would often just have weights going to infinity.
Yes.
So are you safe from this here by some scaling of other quantities? I would think if, for instance, the curvature of the loss exceeds some threshold value, then you'll start jittering out of it to infinity.
I think up to square root of n. I think it's possible to analyze sort of the Lipschitz constant of the loss and that we are stable. I think up to alpha equals 1/2 would be the edge of stability. I think, and beyond that, yeah.
Thank you.
Yeah.
More questions? Otherwise, let's thank Edgar again. And